I know I said I would do some more videos on my 16-bit computer, but I got a bit carried away and built an entirely new design, so that's what this video is about. I'm still working with the same 16-bit main bus, but this is a way more powerful and refined design than the last one. The most important change is in the basic underlying architecture. Here we follow more of a RISC philosophy as compared to the last design, which was CISC. The last computer usually took around 5 cycles for a single instruction. Here a single instruction independently is finished in only 2 cycles. But it gets better. We do 2 of these load execute cycles in parallel, meaning that one instruction is executed every cycle, while the next one is loaded simultaneously. To do this, I needed to adjust the hardware to make loading and executing work in parallel and in just one clock cycle. This added complexity is where most of the extra chips on our new design come from. For example, RAM for data and code is now split, such that we can load the next instruction from code RAM while also using data RAM to execute the current instruction. I made changes like this across the board to make every instruction run in one cycle, which really speeds up the design a lot, even when you run it at the same clock speed as the last one, and as you might have expected, the new design can also go a lot higher. So let's actually run some programs on this thing. We'll start with a program that simply counts up the sort of hello world equivalent of the DIY computer world. No worries, we'll also run actual hello world in the next video. So I can assemble this program using my assembler and then upload it afterwards. Now I just have to press reset to get the counting going. Now if you look at the program, you might be surprised to see a NOP, so an instruction that simply does nothing there. That's actually because of the pipeline. While the pipeline executes the jump loop instruction, it actually fetches the next instruction. The jump hasn't been executed yet, so it doesn't know that the actual next instruction would be the add. So it fetches the instruction after the jump. Well, in the next cycle, that instruction is going to be executed even though we jump back. And so we just have to put a NOP there to make sure that we don't execute an instruction that we don't want to execute that might be there. We can actually make use of the pipeline by doing something very confusing, getting rid of the NOP and then switching the order of the 2 instructions. Now, if you think about what happens, it still counts up, it still does the same thing, because it will first execute the jump loop instruction, and while executing that, it will load the following, the add instruction. Now, because of the jump loop, the instruction pointer doesn't increment, but we still execute the add instruction afterwards because it has been loaded, so it will be executed in the next cycle. But because the instruction pointer hasn't incremented, we sort of start the cycle from the beginning again. And that's how we can make use of the pipeline to actually count faster. I already uploaded the improved version of the counting program. If you actually go through the frames, then you will see that this counts 1/3 faster. And this is really useful for programs that spend a lot of time in small loops, something like a mem set or a mem copy that spends a lot of time in a very simple loop if you do it for large areas of memory. Now let's get to another program, one of my favorites, shifter.s. This program sets a single bit and then shifts it around in a register. And it's not doing that the boring way, using 16 shift instructions or a for loop or anything. It's actually doing that using flags. We have a sign flag that's set when the last bit in a register is set, and we also have a parity flag that's set when the first bit in a register is set. And using these 2 flags, we can shift the bit around. And it's a very nice stress test for these flags, because if one of them fails to set just once, then the bit will be shifted out and the program will get stuck in an infinite loop. Unfortunately, the frame rate really doesn't do it justice. It actually looks really smooth in person. Now I also have a bigger version of that program, shifter long, that doesn't just shift a bit around in a single register, but an entire row of registers, so 4 registers, which also looks really nice. Enough with the LEDs, let's move on to something that my last computer couldn't do. One really cool thing is that we have a USB to 8-bit parallel port converter on board, which just shows up as a normal serial port when you plug it into the computer, and we can interface with this serial port in code. So let's create a simple serial echo program. Here you can see the program. It first of all selects the USB peripheral and then uses bit 7 on the input port to see if data is available in the buffer of the serial port. And if so, then we receive that data into R0 and send it straight back. You can just open PuTTY or any USB serial monitor and open the serial port. and then it will echo whatever you write. You might be thinking that I'm just typing on the computer right now, but that's not what's happening. Every single keystroke is actually sent to the computer over the serial port, which then echoes it back, and this echo is what's being shown. If I, for example, count up, then R0 will count up 2, because numbers in ASCII are just the actual number or together with hex 30. In disguise, I've actually been using this serial or parallel port all along, because in case you wondered, that's actually how I upload programs to this computer. In the very beginning of program memory, there's a little program called bootrom.s that, just like before, takes data from the serial port, but instead of just echoing it back, it takes 4 bytes and puts them together into one 32-bit instruction, and that instruction is then written to program memory. That's how I've been uploading programs all along in this video. Another thing my last computer couldn't do was display something on a screen, at least without an external computer and a program running on it to receive all of the data that my computer sends over, and it was just way too complicated. So I added a little header to install this little OLED screen on the computer, which we can interface with directly using an 8-bit parallel bus. The first program I wrote that actually makes use of the screen just draws a nice looking circle to it, which is actually just an adaptation of a previous program that calculated pi, which are very similar things, at least if you calculate pi in a certain way. Anyways, here's the program running. You might not actually be able to tell that it's doing anything because it's quite slow. And there's a lot of pixels even in this low resolution screen. But fortunately, I can also increase the clock speed on the computer. I can do that with this little piece of code. The oscillator on board has an SPI interface, and using the output port on the computer, I can bit bang that interface and then send it another frequency. The frequency is going to be 2 to the power of whatever we put in this register kilohertz. I mean, you can also adjust it between powers of 2, but I haven't really done that yet because, well, the range is so wide. So let's run this at, say, 100 kilohertz, 0.1 megahertz. And you can see now it actually works pretty well. The maximum frequency it can do is about 2 megahertz. You can see at that point it can basically just render the image instantly. We can actually execute 2 million instructions per second at 2 megahertz because of the pipeline. We can execute one whole instruction per cycle, and that makes this computer quite a bit faster than early microprocessors, which also were oftentimes 8-bit and didn't have hardware multipliers or dividers, so it is quite a bit faster than those. Let's get to an actual fun program. I already wrote Pong for my last computer, but it was kind of bad. The physics was very predictable, the resolution was quite low, and I even had to cheat. The rendering wasn't even done on board because just sending all of the pixels took too much time to run it at a decent frame rate, so it's basically just sending the positions of everything, and the rendering is being done on the computer. Needless to say, with this machine I could make a way better version of Pong. And this is what it looks like. It starts off with the same boilerplate as the OLED sphere code, just to turn on the OLED. Then we have some code that sets the frequency. In this case, it only runs at 16 kilohertz, which is very much the lower end of the frequency spectrum. Then we clear the screen. The frame buffer contains random data in the beginning, and we want a nice uniform black background, so we just have to send a 0 for every single pixel. Then the actual game begins. In the game loop, we first check for inputs on the buttons to move the pedals. Then we move on to physics. We have to calculate where the ball is gonna be, if it collided with anything, and also in case it collided with one of the pedals, well, we have to check if the pedal was actually in the right place, and otherwise the game ends. And finally, we come to drawing. For drawing, I'm actually using a very neat little trick. Instead of clearing the entire screen every frame, which would take way too long, I just store for the next frame what we drew in the current frame. And then in the next frame, before drawing anything new, we just draw what we drew in the current frame again, only in black, thereby effectively clearing the screen. But because we drew to so few pixels, this is a lot faster than clearing the entire screen. You can see when I start the game, the whole screen first of all gets set to black, because it just contains random colors in the beginning. And then the game starts. I can move the pedals with the buttons and just play Pong like you used to. What's pretty incredible is that Pong on this computer actually runs at a lower clock speed than Pong on the last computer. And that just highlights how many IPC gains we've gotten here. How much more we can do in a single clock cycle. So this video was about the hardware and some basic programs in assembly. In the next video I'll show you the C compiler I wrote for this computer.